Another lesson for integration to find antiderivatives. So we have 5.5 here. Okay, now you know how to find indefinite integrals. You also know how to find definite integrals. You also know average. You know the fundamental theorem of calculus 2, 1, right? Now, how do you implement different strategies when integrating? So far, I didn't tell you this, but you've been working on the most basic cases of integration, right? But much like derivatives, you remember how derivatives had chain rules and so forth? Well, you have similar thing for integrals, okay? So, how do you integrate composite functions? Composite functions, as you know, it's like if you have f of x, right? Versus f of g of x. F is not just a function of x, but f in itself has another function attached to it. So you got to take f, but whatever g of x is. So f is dependent on g of x. So I know you thought it was fun and games, but not quite. Okay, so you must, you know how you used to forget the chain rule every time you did derivatives? Well, you must not forget during integrals. Okay, so remember the chain rule? It was something like this. Now, anytime we use an u, we're going to say this, we're using U-Substitution. Okay? It's a technique that we're going to use. It's called U-Substitution. Not me substitution, U-Substitution. Ha, ha, ha. Okay? Bad joke. I get it. Okay? All right. So, basically, f, we're going to let y equal f, which is a function of u. But u, right? So, because f is a composite function of u, and u is g of x. So we take the derivative of f of g of x. Remember that? And then we take the derivative of f, right, which is f prime of g of x. And then we took the derivative of g of prime of x. So this is going over the derivative stuff, right? Remember, it was something like this. We have a square root of maybe, I don't know, 3x to the 4th. This is g of x, this is f of x. So there's two layers, a composite function, okay? Now from the definition of antiderivative, we're going to show you, dun, 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 how does that work for integrals. Let's do that for here, okay? Now, definition of antiderivative is this. You take the integral of, you see this? This is the derivative, right? Because once we integrate, we get the original function, right? So we're going reverse now. We're going to take the derivative, right? Remember the chain rule of the derivative? We're going to have to take the antiderivative of it. So we take, how do we do that? Well, we basically integrate this whole composite function within the integral, and we find something like this, which means we take the integral of f prime, and we get this. Don't worry, it's easier than you think. We're going to use something called U-Substitution, okay? Now, I'm going to show you a definition that's a little bit confusing, okay? Theorem 5.13, anti-differentiation of a composite function. Let f be a function of whose range is an interval I. Let f be a function that is continuous on I. If g is differentiable on its domain and f is antiderivative of f on I, then. So don't worry so much about the theorem in depth. It's basically saying this is true. So you're going to have to remember this, but we're almost always going to use U-Substitution. U-Sub, okay? We're going to use U-Sub, not U-Sub Huang though, just U-Substitution, U-Sub. Let u equal g of x gives du. What do you get when you take the derivative of u, right? Then you get g prime of x dx. Okay? And then you somehow implement it here. So these two, yes, you have to remember, but this is the most important thing. You take the integral of f of u du equals f of u plus c. This is the one I want you to really remember and utilize and also write down, okay? So I'm going to show you a few examples to do this, and I want to prove to you that it's actually easier than you think, okay? Stop the video at any time if you have to stop and absorb and digest this material. Can you recognize f of g of x, g prime of x in this pattern? Okay, so this is part 1. All right, and I'm gonna show you how this is f of u and du. Okay, so this right here is f of u, and this is du. Okay, I'm gonna show you that. All right. Alright, so, okay, recognizing patterns. Let's not even recognize patterns. You know what we're going to do? We're going to just jump right into it. We're going to use U-Substitution here, and I'm going to show you how easy this can be, okay? So you can see there's lots of functions going on. There's a function here, and there's a function here, a composite function, right? So which one looks more complicated to you? This guy here or this guy here? Because one of them you're going to make it let equal u. Okay? So, and you'll see how these are all kind of fixed, so then they kind of work out. Okay? All right. So let's do the first step. We're going to let u equal something more intricate. Well, not even just more intricate, but u is the one that's actually a function within a function. You see how x squared plus 1, you can actually take the derivative of that on its own, but you see how you can actually take the derivative of 4 too, right? Or if you take the antiderivative, you can take the antiderivative of x squared plus 1, but you can also take the antiderivative of this whole thing to the 4th power. So I'm going to let u equal x squared plus 1. I know, it's a little bit weird because you're integrating x squared plus 1, but it's to the 4th power. So let's actually take du, because this is f of x dx, right? So we're going to write everything in terms of u. That's why it's called U-Substitution. Take the derivative of u, which is 2x, and it's dx, I'm sorry. 2x dx, because it's x squared plus 1, which is here. When we take the derivative of this, we get 2x plus dx. But you can see that these are fudged a little bit, right? Because you can see that u is here, and 2x dx is here and here, okay? So I'm going to take a different marker here. You see how 2x dx is all in orange here? And this is our u. So if you were to rewrite this integral, it would be this. Integral of f of u du, okay? Now, so that's our integral that we're achieving, and that's what we said here, right? So what is your f of u that you're integrating? Isn't it u to the 4th power? So you integrate u to the 4th power du. But wait, so let's just make sure. U is x squared plus 1. That's u to the 4th. But what's 2x and dx put together? It's du. So everything that you see here is just used with U-substitution. I know it's a little bit weird, but it'll become a habit, okay? Now you integrate u to the 4th. Everyone in here knows u to the 5th is, so u to the 4th integration, when you add, with the antiderivative of u to the 4th is u 5th to the over 5 plus c. But now you're not done because remember you're solving for x, right? So all you do now is you do substitution. What is u again? U is x squared plus 1 to the 5th over 5th plus c. And that is your final answer. Now, if you're like, what? Don't worry, we're going to do a few and you're going to see a lot of patterns. But you know, how do we check that this is correct, right? How do we check to see if the antiderivative is in fact equal to this, right? Isn't this the derivative of this guy? So do it that way. Do it that way. So again, this one, let's take the derivative, okay? So 1/5 we're going to leave out. We get x squared plus 1 to the 5th power, right? Well, let's take the derivative of this guy. Let's leave 1/5 outside. Isn't this really 5 x squared plus 1 times 2x? Because chain rule, right? You take the derivative of this guy, but you also take the derivative of this guy. So 5x, oh, sorry, I meant the 4th here. Okay? Hey, where have you seen this before? Oh my god, it's the same thing. Hiya. And you're left with 2x, x squared plus 1. Okay? And that's what we were looking for. Oh, to the 4th. And that's what it was. You could always go back and check your answers that way. So make sure you're never like, am I right? You should never ask yourself that. And you never go, oh, I could just look it up in the calculator. Okay? Let's try another one. And I want you to try this one on your own. Just stop the video and see if you can do it on your own. What will you let u equal, right? Okay? The more complicated, but a function that's within a function. So again, x cubed plus 1. Okay, and that means du is going to be 3x squared plus the thing, 3x squared, right? And then it's going to be dx here. Look, again. 3x squared dx, 3x squared. And then you have your u here. Okay, so how do you write this in terms of fu, du, right? So you know it's going to be a cubic root of u du. Everything is in terms of u. Okay, because this is our f of u du. But if you want, again, you should write this as an exponent, and it's easier for you to integrate. When you integrate this, you're right, you get u to the half, right? You have to add 2, 3 over 2, 2 over 3, plus c. Don't forget to replace the u, substitute for u, and what do you get? 2 over 3, What's your u? Your u is x cubed plus 3, x cubed plus 1, I'm sorry, 3 over 2 plus c. And how do you checky your solution? All you have to do is take the derivative of that. Make sure you get this guy here. Okay, stop the video and make sure you can do c on your own. Okay, try c on your own. Go ahead and do that. Let u equal what? Let's du equal 2. Okay, welcome back. Which one did you let equal? Check your integral sheets, and I hope you did tangent x plus 3. Because the derivative of tangent x is secant square x dx. All right, we're ready to start. Integral of f of u du, right? So that means f of u, which means what? So I'll write that again, f of u du, right? What's your f of u? Isn't it just u in this case? Because this is the u, this is u, and this is part of du, right? That's how it makes up this little expression here. So it's going to be du. And what's the integral of u? Isn't it just u squared over 2? And then plus c, of course. And then you just plug in for u. And u is tangent x plus 3 squared over 2 plus c. Okay? All right, now I'm going to ask you to try the next 3 on your own, okay? Next 3 on your own. I'm going to show you next 3 on your own, and we'll check the answer together in class. See you later, alligators!